See if I can move windows around. Okay, so any administrative things before we start?
I believe someone had a couple questions in the chat.
Yeah, Scott, we can just, if you want to figure out where your particular grade is, just come to office hours and we can go through your test scores and quiz scores and things like that. But the grading scale for the second exam, or the exam 1 second try, should be about the same as the first one. And somebody said, when is the next exam? It's on the syllabus. It is Tuesday, April 20th. So what is that? That's a week from next Tuesday. Okay, and the chapter we're on now is the last chapter that's on that test. So it's chapters 9 through 12 in the open source book. All right, so it's been a while. So let's go back just a little and remember where we were. So where we left off, we were doing problems with the Biot-Savart law. And so, right, we wrote down Biot-Savart, which again, be careful if you're looking at other sources, you'll see this written differently. I'm going to follow the notation of your book. Right. So this tells you that this essentially is the encoded form of the phrase currents cause B fields. Electric charges cause electric fields. Electric currents cause B fields. So if I have a wire like this, and I say, and it's carrying some current I, and I know we talked about this, but I think it's worth just going over it a little again. And if I have a point in space here and I say, what's the B field at this point? Well, according to this, it's mu naught times I, which are both constants because I is the same at all points in the wire, over 4 pi. And the integral over all current elements. So it's much like what we did with the charge distributions, right? Every piece of the charge distribution contributes to the electric field. And here, every part of this current distribution contributes to the magnetic field at a point. So here's the point where we want the B field. Here's a little segment of the wire here. This has some vector, ds vector. So the direction of ds vector is in the direction of the current, and then it's just a short length. So for this element, ds vector points that way. R hat points this way. Actually, to follow the notation in your book, I think they use, I can't remember if they use script R or regular R, but I guess I wrote it as regular R. And so that's R hat. And then this length is R squared. Okay, so this particular element wouldn't really contribute anything. Yeah, Evan. Evan, can you do me a favor and send me an email? But then, yes, I'll post an old exam. So for this particular element, ds, it's R squared. It's R hat squared, not R. Yeah, so it's R hat, but R squared. Does that make sense, Gavin? Oh, I'm sorry. Yes, thank you. The distance is R, not R squared. Yes, thank you. I'm a little underslept today. Right, so it's not R hat. Yeah. Thank you. Okay, so the B field at this point from this element we're going to have to cross ds vector with r hat. Now, in this case, that's going to be easy because magnitude of ds vector is ds, magnitude of r hat is 1, and the sine of the angle between them is 0. So this will be 0 for this one element. That doesn't mean the B field here is 0 because this is not the only piece of current in this wire. The B field here from that element, this contributes nothing to the B field here, but there are lots of other current elements that do contribute. So here's another little current element. In this case, ds vector points that way. R hat now points this way. And then this length from there to there is now R. So you get some contribution to the B field here from this element. And if you want the total B field here, you'd have to integrate over all of these current elements. And to do that, you'd actually have to know the exact shape of this wire and how much current is in it and where exactly this spot is. And so we did a couple examples. I don't want to redo this one. The first example we said there was a current I in a wire of radius R, and we found the B field at this point at the center. And the one thing I do want to review in this is that if you look at this current element here, ds vector points that way, R hat points this way. So ds vector cross R hat is out of the page. So the B field here from this element is out of the page. The B field here from this element is also out of the page because ds vector points this way now and R hat points that way. So ds vector cross R hat is also still out. So all of the elements contribute an outward B field here. And if you look at it, the size of the B field from each of these elements is the same because they're all the same distance away. 1 over r squared doesn't change. And so we were able to very quickly derive that the B field here was equal to mu naught I over 2r, and then we said out of the page, so we'll just call it out hat. So the B field at the center is equal to that, okay? So that was a short example we did, and then where we stopped, we were right in the middle of a longer example, a sort of a more complicated one. Any questions on this first, though? All right. So the longer problem that we were in the middle of, I think, and we kind of rushed through the end of it, so we're going to do it properly now. We're going to say you take a long straight wire, and we're going to use this result a lot. And we'll say you have this wire is carrying a current I this way, and I want to know the B field here at this point P, which is a distance capital R away from the wire. Well, we're going to do the same thing we've done before. We're going to say, what's the B field here from an arbitrary element? Let's just pick this one. So this has a vector length, so we'll call it ds vector. And let's say that this is x equals 0. And we're looking at this arbitrary element that is a distance x up from the origin. All right, so we're going to need to cross this vector with r hat vector. So r hat vector points from the current element to the point we want the B field. So this is r hat. And now you can see why this one is trickier than the circle, because each of these elements is a different distance away from here. So the elements in here might contribute more, plus the angle between ds vector and r hat keeps changing, because for this element here, ds vector is like that, r hat's like that, so it's 90 degrees, but it's not 90 degrees for this element. So the angle keeps changing and the distance keeps changing. And so this one, the integral is not going to just drop out like it did with the case of the circle. Right? So what we know is that B is mu naught I over 4 pi. The integral of, I'll tell you why I'm changing to dx in a second, dx vector cross r hat over r squared. So this vector ds, if this is the x-axis, ds vector is the same as dx vector, right? This vector move is pointing in the x direction. So I can just call it dx vector. And I'm going to integrate from x equals 0 to infinity. And I think we had this part last time when we stopped. And you say, well, wait a second, that would only include the current elements from here, from x equals 0 up to infinity. What about the B field contributions here from all of these elements? Well, those would be the same. The contribution from this element will be the same as the contribution from its partner on the other side. And so we can integrate from 0 to infinity and then just double the result. You could also integrate from minus infinity to infinity and not double the result if you prefer. Okay, and this is the direction of this thing. We'll have to find when we do the cross product here. Right? Okay, so we're going to have to label a couple angles here. So B is going to be equal to mu naught I, I'm going to bring this 2 in, over 2 pi. And now we're going to integrate from x equals 0 to infinity. I need this cross that. So magnitude of this is dx. Magnitude of that is 1 times sine of the angle between them. So it's going to be dx times sine of theta, where theta is the angle between them. Except what is this? We got to correctly label this angle. The angle between them is this vector. That's theta. So I need sine of this angle. But sine of this angle is the same as sine of this angle, right? This is 180 minus theta. So sine of this and that are the same thing. And I need my 1 over r squared here. And I also need to make sure I do the direction. So dx vector cross r hat is, using the right-hand rule, is going to be into the page, right? Because this is not equal to that, because this is a number and that's a vector. So this is not equal until I get my direction right. And so I'll call it in hat. So what's in the numerator here is exactly the same as that. That's the only thing I really changed going from there to there, other than carrying that factor of 2 in. Yep, Ender, exactly right. 0 to infinity is only half of what needs to be integrated. And that's why I said, well, let's just do this half and then double the result. Is that okay? Oh, and I guess Phi had the same question. That's where the factor of 2 comes from. All right.
Can you explain the in hat quickly? How you got that again? Sorry.
Yeah, no worries. So ds vector point, I can't do it up here because I'll be off the page. Well, here, actually.
Was that just the right hand rule? Is that all you did for that?
Yep. ds vector points this way, r hat points that way. So do a cross product of black cross red.
Sure.
In.
Okay,
so
thank you.
That came there.
Yeah.
Okay, good. What else? Other questions so far? Is ds always the same as current flow? Yes. Yep. Asa, yes. What else? Saad, did you also, Evan also asked that. Does it make sense now or no? The in hat? Yes, okay, good. Okay, good. So now we're making progress. Now we just have to write, I mean, we can't integrate this yet because right, x equals 0 to infinity. You can't pull this out and you can't pull this out either because, right, sine theta, this angle is a function of x. Remember, x is where you are as you're moving and looping over all these elements. X is where you are, but sine theta is a function of x. Obviously, this angle changes depending on which element you're looking at. And r squared, the distance from the element to the point, that also is a function of x. So we've got to get both of these in terms of x, and then we'll have an integral we can do. Okay, that's not going to be that bad. So we need sine of this, which is same as sine of that. And sine of this is going to be this over this. And this length is going to be square root of x squared plus r squared. Okay, so let's just rewrite this. So this is going to be mu naught I over 2 pi. I'll pull out the in hat. No reason to leave that inside the integral. Integral from x equals 0 to infinity dx over r squared. R squared is going to be x squared plus capital R squared. Right, everyone okay so far? Yeah, Connor, give me just a second for that. It's always ds to r using the right-hand rule. Jeff, yes, right? So it's dx vector cross r hat. You got to make sure you get the order right. So dx vector goes this way, r hat goes that way. So the cross product is into the page. But you got to be careful, because if you do cross product of this with that, then it's out of the page. So a cross b is negative b cross a. In terms of direction, the size is the same, but the direction switches. Okay, good. So this, I've got r squared in here, and I still have a mistake. I need sine theta, or sine of 180 minus theta, which is the same. So I need sine of that angle, which is sine of this angle is going to be this over that. So that is r over square root x squared plus r squared. Okay. Now, if you look, right, capital R that's a constant, so that can come out. So this is going to be mu naught I R over 2 pi integral from x equals 0 to infinity. And then I'm just going to combine those and write this is x squared plus r squared to the 3/2. Okay. This is one of those hideous trig sub integrals. And so, well, actually, let me stop there. At this point, all the hard work of the problem is done. At this point, it's just, look up or do the integral yourself. Looking it up is fine. But the hardest part of the problem is is in here, right? So once we get to here, now we're just going to do the integral and finish up. So
Just
think
real
about
quick.
questions getting to here. Yeah.
Just real quick, could you explain again where you got r over radical x squared plus r squared?
Yeah. So if I have a right triangle, A, B, this is square root of a squared plus b squared.
Oh, wait, that's what sine theta becomes.
Yes.
That's just sine theta. Okay. And then how do you get the x squared plus r squared underneath the dx? Is that just what r squared is? Yeah. Okay.
Sorry, where this came from?
Answered my own question. Never mind. Thank you.
Okay, yeah, very good. Is the hat still outside? No, I moved. Oh, yeah. Thank you. I accidentally forgot to write it. In hat. Good. Thank you, Jeff. Would we be, Allison, looking up, crazy integrals. If there's a crazy integral on the exam, if you look at the formula sheet, there's a bunch of integrals on them. I'd always make sure it's either on that sheet or I'd put it on the test paper itself. So yeah, you don't have to you got to know how to do simple use substitutions, polynomial things. Those you should just be able to quick do on an exam. But if it's crazy integration, I'm fine with you just looking it up. You can't really, an exam, you can't leave it like this, because this is not, if you say, what's the B field here? That's not really that's not a B field. I don't know. I don't know about point. Okay. And then somebody had asked, Connor, I brushed off your question before, and now it's drifted backwards. Hold on. Does a magnetic field always rotate clockwise with respect to its direction? So Connor, yeah, there's a tricky, I don't know if it's a tricky thing about it, but actually let me get to that question once we get the answer. We're gonna get there in a minute. Okay, so if you look this integral up, this is of the form integral of dx over x squared plus a squared to the 3/2 equal to x over, so the indefinite integral a squared times x squared plus a squared to the 1/2. I think this is one of those 2 arctan u sub integrals. Okay, so good. So now you can just use this result in here for this integral, plug in the limits of 0 and infinity, and if you do that, you should wind up with b, and you should do this on your own if you're at all shaky on this. Mu naught I r over 2 pi x over r squared times x squared plus r squared to the 1/2 infinity to 0. And if you plug those limits in, you'll get mu naught I over 2 pi r in hat. All right. Okay, so so good. So we derive that the B field here, let's just take a look at what we have. The B field here goes into the page, and it drops as 1 over your distance away from the wire. So it's constant times 1 over r, and it increases linearly with current. Drops linearly with increasing distance and is into the page. Now, Connor, you had asked about, and it's a good question, right? About what are the directions? Is it always rotating around the wire? I don't really want to use the term rotating, right? Because there's nothing moving, but it is true that if you have a wire with current I going this way, the B field, what we just found, the B field at this spot is into the page. So let's mark that with an X. Right? Okay, and so at this point, I think it's useful to just try to guess what the B field is elsewhere, right? What we just showed. Now, right? You imagine picking this thing up and looking at it this way. So if the current is going up, so all I'm doing is picking this diagram, this wire with current going that way, and B field into the page. I'm just lifting them up here. So if the current is up, the B field at this spot points that way, sort of toward the camera. So if you had to guess, what would you guess was the B field over on this side? Now you might guess, well, maybe it's also in toward you, but that'd be strange, right? Though basically it would violate common sense symmetry if I have a wire with current going up, if the B field over here pointed at you and the B field over here also pointed at you, that'd be kind of strange, because how would you decide which is this preferred direction for a current going vertically up? Is it like, why this way? Why not toward me or that way? And what if I twist the wire 90 degrees? Does it know that it somehow needs to have the current go this way now? Because it's just a uniform current going straight up. So there's no way to choose one particular direction. And so it shouldn't surprise you too much that if you're here on this side of the wire, the B field goes like this. If you're over here, the B field goes this way. If you're here on this side of the wire, the B field comes toward me. And if I'm here, the B field goes to the right. So I don't really want you to think of it sort of swirling around, because there isn't, right? There's nothing moving, but it is a fact that if you're here, the B field is out of the page. If you're here, it's in. If you're up above the current, it's to the right. And if you're underneath the page, it's to the left. Or if you're standing here looking down at the wire, so the current is coming out of the page, now all we're doing here is we've picked this diagram up. And so now if we lift this, right, the B field is into the page, the current is that way. So now I'm lifting it so you can see it from this view. The B field over here is this way. The B field over here is this way. The B field here is that way. The B field here is this way. And you can see that from this dx cross r hat. If you're standing here, dx vector points this way, r hat points that way. So dx cross r hat is into the page. So the B field here is into the page. If you're on this side though, ds vector points this way, r hat goes that way to this point. So now ds cross r hat is out of the page. So the B field on this side, on the surface of the paper, is out. And you can do that same exercise going all the way around. And so there's a trick to help you remember this, although it causes some people, I don't know if it helps everybody. The B field the current is out of the page. If you put your thumb in the direction of the current, the B field will loop around. And so if your thumb goes this way, the B field here is that way, here it's this way. Let's see, Dan, I'll look and see what's on the formula sheet. There should be integrals. If not, I'll add them. Exam 2, it's Taha, just, yeah, look at it's on the syllabus. Okay, so questions about directions or about solving this?
Yeah, thanks. That makes a lot of sense. I was just thinking about it like as marbles hitting against a cylinder or something. I just want to know I was just trying to think in my head which way the cylinder is turning.
Right. Okay, good. What else? Other questions? Okay, so there are a couple other, I think there's one other Biot-Savart law problem in the homework. And so we're going to shift gears just a little, and we're going to use this result that we just found to find the force between parallel currents. Okay, so what we know is that if I have a wire carrying current I, and it's in let's say this thing has let's say I have a wire of length L, and let's suppose that it's in a B field that goes into the page. Okay, you know there'd be a force on this, and take a second to figure out the direction of the force on it from the Lorentz force that we looked at from last chapter. Force is I times L cross B vector. So this is a wire carrying current I of length L. I know the wire has to be long, has to continue if it's carrying current, but let's just say we're focused on a section of it that has length L. So I L cross B, L goes this way in the direction of the current, B is into the page, so L cross B is left. So there will be a force to the left Okay, and I guess B and L are perpendicular. So in this case, the force would be equal to, if this were the X direction, the force on this wire would be I. Magnitude of L vector is L, magnitude of B vector is B. Sine of the angle between them is 1. So it'll be ILB, and the direction is that way. So it'll be minus that x hat. Okay, so good. So that's the force on a wire of length L carrying current I in a B field B. So that's kind of a review from last chapter. So now we're going to do almost the same problem. We're going to just say, well, where did this B field come from? Well, suppose that you had two wires. I have let's call them wire 1 and wire 2. And the perhaps the most important thing about to grasp about this topic is it's nothing new. We're going to just basically use the same IL cross B result that we had last chapter and the result that we just derived for the B field near a long straight wire. Right? So the question is, let's say this one carries a current IA, and let's say this one carries a current IB, both up. So the outline of what we're going to do is we're going to say, look, this wire is sitting in a B field. And it's sitting in a B field because it's a distance, some distance away from this wire. Let's give these things distances. Let's say it's a distance D away. And let's say that each of these wires has a length of L. So the basic idea of the problem is that this wire produces a B field where this wire lives, right? It's just like, it's the equivalent of you have, some charge Q1, another charge Q2. What's the force on this charge? Let's say they're both positive. The force on this charge from that charge, you say, well, this charge produces an electric field at the location of Q2, and Q2 is now in an electric field, and so it feels a force of whatever the electric field is. So it would be K Q1 over distance squared. That's the electric field at this charge because this one exists. And then the force on Q2 would be equal to the E field that it's living in times its own charge. And in this case, it'd be X hat, right? So that's going way back, and it's the same thing that we're going to do here. We say this wire is living in an electric field that's caused by this wire, and a wire carrying a current in an electric field will feel a force on it. All right. So good, let's find that out. There's a B field at this location from this wire that goes into the page. Because, right, this is a current going up, so the B field on this side of this wire is into the page. Okay. Questions so far?
And why is it into the page again?
Yeah, so if you look back at, so we derived from here, so this was the problem we just did. If you're on this side of the wire, carrying current I that way, the B field here is into the page because you've got ds for each element, you've got ds vector cross r hat. And the cross of this and that is inward from the right-hand rule.
Okay.
Okay, so it's an inward B field here from that, from the existence of this current. And we already said that B is equal to mu naught IA over 2 pi d. So that's the result we just derived. So B at location of wire 2, right? Mu naught times the current in this wire divided by 2 pi times the distance. That's what we just derived. So the force, wire 2 feels a force. So same thing we just did, right? You've got a wire carrying current IB in a B field of this strength, and IB cross B, which is into the page, is going to be left. So it's just, again, this problem we just did. The only difference is now we actually know how strong a B field this wire is in. So wire 2 feels a force to the left. And the size of the force, so F on wire 2 is going to be the current in wire 2 times its length times the B field that it's in. So that's going to be I sub B, the current that it's in, and it's going to be negative X hat. So I'll put that's a minus. The current in the wire times its length times the B field that it's living in, mu naught I A over 2 pi D. And that's going to be, so then it's negative to the left, so it's negative X hat. So if I just rearrange this will be mu naught IA IB L over 2 pi D. That should be negative X hat, if this is the X direction. Okay, so think about questions on this for a second.
Can you go over where you got like each variable and the force on wire 2 equation, like the negative B, the L, mu naught, and all that stuff?
Here?
Yes.
Yeah, so again, go back to here. When you have a wire with current I and its length is L and it's in a B field B, I don't care what, any B field, that's the force that'll be on it. You okay with this part? Whoever asked, is that okay?
Yes.
Okay, so now we say, okay, good. So now we have a wire, and this is all about breaking the problem up, this problem up, so it looks like this one. You say, good. Now you have a wire that's carrying current IB, and its length L is L, and it's in a B field that's equal to this, because it's near another wire. So all I did was say, okay, I picked this up, and I said, all right, we want the force on this wire. The current in the wire is IB, its length is L, and the size of the B field that it's in is this, because it's a distance D away from this wire. So this, what I've written down here, if you look, it's exactly the same as what we had here. The only difference is here, I just said, oh, from somewhere, from who knows from what, this wire is sitting in a B field B. In this case, I say, well, it's actually, you got to figure out what the B field is. It's sitting near another wire. And so you find the B field that it would be in, and then you go back and you redo this. So it's just I, its current, times L, its length, times the strength of the B field that it's sitting in. And I just rearranged. Is that okay, whoever is asking that?
That makes fantastically sensibly word. Yeah.
Okay, good.
English 101.
Let's see, I have one more question. Could I just say, so wire 2 feels a force from the left, or does it have to be like, is there a reason why it's to the left?
No, I would not say, it does not feel a force from the left, right? Things don't know, right? They're not sentient. And so it's, right, it's a common mistake. You can get into trouble thinking about where, forces from something. Objects have forces on them. So you would write a force vector, the point on the object that goes this way. Right, like if I put a wire on this side and had its current go the other way, it would also have a force that goes this way. And so I would say it's not just a matter of fussiness, just worry about the direction of forces on things, not from. If that makes sense.
So at this point in the game, are we fair, or are we allowed to, at this point, like say the equation for B and use that equation for B? Like we already derived that, right? So if we get a question like that, we can just use that equation since we know it.
Okay. Yep.
So when will we have to derive it? Will the question like essentially just say derive the equation for B using?
Yep.
Okay.
Yep. In fact, that was, I don't know how many, some years ago, I just put that straight on the exam, exactly as we did. Derive the B field from a long straight wire.
Oh.
So in that case, obviously you can't say, oh, the B field from a long straight wire is that, right? Then not derive. So, okay, so other questions so far? Okay, so let's look for, we're not going to redo this the whole way, but I want to practice directions, and to get practice yourself, you should try this one. Find the force on this wire from this one. Right, so this is the same as we just found the force. If you find the force on Q2 from Q1, you'll get this. If you then say, okay, find the force on this from that, you know you'll get exactly the same thing. It's just the E field here from this will be KQ2 over D squared. And then you'll have that times Q1, the charge. And so these will just reverse places, but the force is the same, which it needs to be. If this is applying some force to that, then this has to apply that same amount of force to this. But you should on your, I'll explain it quickly, but you should on your own do it in detail. Find the force on this from that. The B field at this location from this wire. So we have a wire with current IB going that way. The B field on this side of this wire is going to be out of the page, out of the page. And so now you have this wire living in a B field that's coming out of the page, right? So there's a B field that comes outward here, caused by the existence of this wire. So now you got a wire whose current is going this way in a B field that's coming out of the page. So now when you do cross of L cross B, it's that way. So there will be a force on this wire to the right. And if you work this through, what you'll see, of course, the B field here from this wire will be exactly that, except with IB instead of IA. And then when you do this, instead of multiplying by IB, you'll multiply by IA. And so IA and IB will just switch places, just like they did here. Right, so the force will be exactly the same, except it'll be in the opposite direction. So these two wires will pull toward each other, right? Okay, so think about questions for a second. Okay, let's do a, let's do a little bit more complicated example of this, just to get a little re-practice with vectors. Okay, let's suppose you've got 4 wires. And so this has a current I coming out of the page, right? So the dot means it's coming out of the page. We'll call it wire 1. Another wire, 3rd and a 4th. Let's label these wire 1, 2. And just for first example, let's keep all the currents the same. Okay, this is supposed to be a square array. And let's say the distance between these is just A for now. Okay, let's find the B field. At wire 4, okay? Again, this is where, and this is what trips some people up on exams or quizzes or whatever. You really want to break problems down back into sort of the element problems that you know. And so as soon as you see this, the first thing you want to do is go back to something easier. And you go back to this idea. If I have a wire carrying current I, and I'm a distance D away, the B field at this spot from that wire is going to be this way. Current's coming out. So B field over here is that way. And the strength of the B field here would be mu naught I over 2 pi D. And I guess it would be in the y hat direction if this is X and Y. Okay? So this is basically the same problem, except you're going to have to do this 3 times, and you're going to get a vector from each one. And then you'll have to add the vectors to find the total B field at that wire. All right. So questions on what we're doing? Yeah, are the wires pointing in and out of the page? Yes, the wires are going, along straight at you, and the dot means that the current is coming toward you. And if it were an X, that would mean the current is going away from you. So that's the same notation your book uses, and most everything uses. A vector that comes toward you is a dot, and a vector something that moves away from you is an X. Okay, so let's find the B field here. So we're going to do the same thing we did before. So B field, let's call it B field from wire 1. So this means so B sub 1 means the B field at wire 4 from wire 1. All right, let's call this the X direction and this the Y direction. So you take a second and on your own page, write down what the B field at this wire is from this wire. We're gonna have 3 contributions. We'll have a B field here from this, from that, and from that. So let's just do them one at a time. So B, right, so this is the B field from wire 1. That's what I mean by the sub 1. So take a second, write it down, right? We're just going to use this over and over. All right, somebody unmute and tell me what the answer is. The B field at wire 4 from wire 1.
It's going to be mu naught I over 2 pi a.
Yep, except somebody help him. There's something missing. It's the same thing I always forget.
X hat.
No.
It would be X hat.
Negative
No.
X hat.
No.
No?
So again, so this is where you want to go. As soon as you get confused, you got to go back to a problem you already know, right? So the B field at this point from this wire, forget about these 4 wires. The B field here from this points that way, right?
Oh, Y hat.
Yeah, so it's Y hat. And if we were over here, it would be negative Y hat. Okay. All right, so questions on this?
Can you explain why Y hat?
Yeah, so if you go back to, right, if you go back to this, so, right, the B field here from this element is ds vector cross R hat, and so it would be into the page. And over here, it would be out of the page. And so we did this, we wrote it like this. And then we said, well, let's look end on at this wire. Let's just pick this up and look at it like that. In which case, you're now looking at this diagram. The current is out. And so the B field over here goes that way. Here it goes that way. So it's really just ds vector cross R hat for different locations that you could be standing. And the simple trick to do that is you put your thumb in the direction of the current and your fingers will curl in the direction of the vector field going around it. And so in this case, current is coming out of the page and we're standing over here. So the B field is that way. Over here, it's down. Is that okay, whoever asked that?
Yeah.
Okay. Okay, so let's see. The next easier one is going to be B from wire 3. Right, so B from wire 3. Take a second and figure that out. I want B sub 3 means the B field at wire 4 from wire 3. So go ahead and write something down and get the direction right. Don't call it out yet. Let everyone think about it. Forget about the other, this and this. You just want the B field here from that wire. I mean, you know it's going to be mu naught I over 2 pi a. And then the trick is to get the direction correct. All right. Anyone want to chime in with the direction?
Negative X.
right, negative x hat, exactly. So this, yeah, negative x direction, so it'd be this times negative x hat. Okay, so questions on this? All right, so now the last one, B2, the B field here from this will be mu naught I over, now we got to be careful, it's 2 pi times this distance. So that's square root of 2a, right? Distance from there to there. And now take a second and think about the vector. This is the size of the B field here from that. And now you got to multiply this by a vector of length 1, but it's not x hat or y hat. So first use the this right hand trick to, in your head, figure out what direction the B field goes here from that, and then write it as that direction as a vector of length 1. All right, any ideas?
It would be towards wire 1.
No, I don't think so, right? So imagine, picture this again. So if you're here, so if I have a wire coming out of the page, right? So here's my current coming out of the page. My B field here is that way. My B field here is this way. My B field here is going to be that way. Right? My B field over here will point that way. Here it would point this way. So I think the B field here from this it's going to point up and to the left.
Yeah, that's actually what I meant. The way I was thinking of it, hold on, if I have my camera here, yeah. So I actually use my 2 fingers like this to represent my vectors. And I was thinking of it in the middle of the square.
Yeah.
So if you were at a point in the middle of the square, you'd be going towards I.
Yes.
Towards
yes.
vector 1. So that's where I was.
Right. Okay. I see what you were saying. But I would say be careful. You always want your forces and directions on the thing that they are acting on. But yes, I get it. So yeah, and somebody chimed in with, so Daniel, your answer is definitely in the right direction. It's the right idea, but there's a problem with it. So you're writing minus x hat plus y hat. Thank you. That's progress, but there's something wrong. There's something wrong.
Is it the cross between them?
No.
You
So
just
here's a
divide-
question. If your car were stuck, would you rather have, now your friends are very weak, let's suppose, you have one friend who pushes with 1 Newton that way, another friend who pushes with 1 Newton this way, and you're stuck in the snow over here. Would you rather have this? Or would you rather have somebody push with 1 Newton of force this way?
Pushing like that will give you a bigger vector in the end.
Yeah,
Like that's
which
the upper
one?
way.
This, yes. So this is actually more force than this one.
It's going to be equal to the hypotenuse using the forces as the legs of the triangle.
Right. So this is equivalent to having one friend push on your car with square root of 2 Newtons this way. This is the same as that, but this is not the same as that. And minus x hat plus y hat is a vector of length square root of 2. Right? Because it goes 1 this way and 1 that way. And so its length is root 2. So you got to undo that extra factor. So this is fine in terms of direction. This is in the right direction. But if you write minus x hat plus y hat, you've just scaled the force up by a factor of square root of 2, which is wrong. You can't just adjust. You can't just change the size of the B field.
So just like computing a triangle, would it just be the x hat squared, negative x hat squared plus y hat squared?
Well, no, what it really is you want a vector of length 1 that points in this direction. So you have a vector of length 1 that's 45 degrees from horizontal. And so what are the components of this vector? It has a length of 1 and it does point in the same direction as this vector, but it only has length 1. And so this has a length of 1 over root 2. And this height is 1 over root 2. And so the vector that points in this direction and has a length of only 1 is minus x hat over root 2 plus y hat over root 2. Or square root of 2 over 2, same thing. So yes, Alistair, same.
Wouldn't you be able to just put that as negative x hat plus y hat over radical 2?
Yeah, yep. Yeah, I just wanted to do it this way to be extra clear about what's happened.
Okay.
I don't get why it's not just over normal 2, because you're just dividing it by half, because it's going like diagonally to the up left. I'm just confused.
Yeah, but right. So it's not because if I say, look, you've got a vector of length 1 that points this way. Break, and this is 45 degrees. So I could call, there's nothing wrong with saying that's 1 times v hat. This is the v hat direction, let's say. And this is a vector of length 1. But now you said that's not very useful because I'm going to need to add this to x and y vectors. So break this vector of length 1 that points this way into components, into some amount of x hat and some amount of y hat. You would have to say its length times cos 45, that is its x component. So it's 1 over root 2 or square root of 2 over 2. This length, if this length is 1, this length is 1 over root 2. And if this length is 1, its vertical component is also 1 over root 2. Distance formula, breaking down a diagonal into x's and y's. Yes, Alistair, yeah. So whoever was unmuting and asking about the half, does that make sense?
Yes, it does.
Okay, good. Okay, so now as Eric pointed out, we could just pull out this root 2. And so let's just do that to simplify things. So this will give us a mu naught I over, let me leave this other 2 pi a. And now we'll have minus x hat over 2. I'm just grabbing this and putting it together. X hat over 2 plus y hat over 2. And you say, well, why don't you just pull this out and put it with there and make a 4? Because then it makes it easier to just pull out this factor at the end. Right? So if you, now we're good. Now it's just a matter of adding components. So the B field total at wire 4 is going to be equal to mu naught I over 2 pi a. And so we're going to have plus y hat plus another y hat over 2 minus an x hat minus x hat over 2. So it'll be minus 3 halves x hat plus 3 halves y hat. So I'm just adding this and that and that and that. Okay. All right, so take a second and think about questions on that.
Shouldn't there be more to that? Wait, real quick. The wire from 3, is that negative mu naught I over 2 pi a?
Yeah.
That is. Okay. Now
Yeah,
I didn't
because
see that.
Again, think about the B field at this wire from this one. Because now this wire you're above, here's the wire, and you're standing here. So the B field here from this wire points that way, right? Go back to this.
And that's just to avoid a negative. That's just to avoid a negative x hat. Because I had it as negative x hat now.
Oh yeah, I mean you could there's nothing wrong. You could write mu naught I over 2 pi a times negative x hat. Sure.
Yeah, but because it's negative, that's why in our answer we have basically those two canceling.
Yes.
And we're just left with the from 2. Okay.
Hey, Professor.
Yeah.
I'm kind of struggling to really understand this problem. Would you mind just spending like an extra 30 seconds explaining like B1 and B3, like how you got the directions?
Yeah. So again, and this is a hard part of this problem, but once you sort of sufficiently break it into pieces, it's not too bad. The thing you have to get any of these is forget about all this 4 wires and just think about this problem. If I have a wire with current I coming out of the page, the B field over here points that way. The B field here points this way. B field here points that way. B field over here points this way. Okay, are you okay with that part?
Yep.
So now, basically, that is the same thing. So if I put a wire, here, this wire sees a B field that points to the left. If I put a wire down here, this wire sees a B field that points to the right because of the existence of this one. Is that okay?
Yes.
Or no? Okay.
Can you say that one more time?
Yeah. Because I already know that the B field up here points to the left, I don't care if there's a wire here or not. The B field at this point in space from this wire points this way. So if I put a wire here and say, well, what B field is it in? You already did that. The B field up here above this wire points to the left. If I drop a wire here and I say, what direction is the B field that this thing sees? Well, you say, look, it's that way. Right? A wire sitting here would see a B field that points this way. That's not a B field that it's creating. That's just the B field that it's sitting in. Just like if I have a charge here, plus Q, and a charge here, minus Q, and I put another point in space here, there's an E field at this point from this charge that points that way, an E field at this point from this charge that points that way. And if I want the total E field here, I got to just add them. So in this problem, we're just applying these directions over and over. And I get it. It's the directions that make it hard. Right? We're just saying, look, this thing sees 3 wires nearby it. It sees this wire here sees a B field from this one that points that way because we're above it. This wire sees a B field from this. If you look, where are we relative to this wire? We're off to the right. So the B field here from this wire points that way. And that's where this Y hat came from. B field at this point from wire 1. B field at this point from wire 3 is this way. So it's minus X hat. And the B field at this point from this wire is this crazy direction, half and half.
Okay, that makes more sense. Thank you.
Okay, good.
Wait, so for B3, right? If you're going from 3 to 4, right? It's going straight up, right?
No. Don't think, don't. This is not like E fields.
Okay.
You're saying there's a wire 3 here, and there's this wire 4. The B field at this location in space, caused by this wire being there, is this way.
It's to the left.
Yeah. So that's why we got a minus X hat on it.
Okay.
Can you draw the big circle of like fields around number 4 so I can see what it looks like?
Yeah. So, the B fields around. Yeah. You want the B fields caused by 4?
No, like the one that's creating. So like the big circle. So at the right, it would go up, and then at the top, it would go left.
Yeah. Let's do it on a separate. Just as getting.
Or
So the B field at the here. Let me just label them again. So 1, 2, 3, 4. So there's a B field here from this wire, which should be this way. So we'll call that, let's just label that 1. So the red means this is the B field here that's caused by wire 1. Is that okay? Is this what you're asking or no?
Thinking of this backward this whole time. Okay, now it makes sense.
Right. And so for anybody else, let me just finish this. So the B field here from this wire is going to be this way.
Wait,
B
how is
field-
the B field? How's the B field by 1 going upward? If we look at that circle, right? If we go to the circle that you drew, right? Why is
Yeah.
it if because there's an arrow going to the left? I don't know how it's going up. That's where you're losing.
Yeah. There is no arrow going to the, no, this going to the left. This is the B field here caused by this wire.
Okay.
The B field here caused by this wire is that one.
And how are you getting up though? That's where I'm confused.
Am I getting this?
Yeah. How are you getting up? Yeah.
Yeah, well, so go back to here. Forget about this whole problem. I have a single wire with B field with current coming out of the page. What's the direction of the B field here?
Right there.
Yeah, right here in space.
Would it just be going up following that
Yep.
diagram?
Yep. And now this is exactly the same thing you've got here. You've got a wire with current coming out of the page and you're standing off here straight to the right of it. Your B field is going to point up.
Oh,
Right?
Thank
This
you.
doesn't know that it's part of a problem involving 4 wires. All you know is that there's a current coming out of the page here. So the B field here from this is that way.
it took me forever to see it, but I finally see it. Sorry. Thank you.
Yeah,
Thank you.
this is one of those things, once it hits you, you're like, oh, right. And so then the B field here from this, you're basically in this situation. You're up here, off to the right and up. And so your B field here from this will point that way. 4 is the reference point. Yes, Alistair. Meaning that's the point at which we're interested in what the B fields are, because the question is, what's the total B field here? Well, the total B field here has contributions from the B field from this one and that one. And so you got to say, well, there are 3 B fields here, like these, and then you got to add them up. This is poorly drawn. This should be shorter, right? Because the B field from 2 is less because it's farther away. Right?
Quick question. So if let's say the current were pointing into the page, then the circle, the B field would be going in the other direction, right?
Yeah, that's a very good question.
Okay.
Well, it depends. If I switch the direction of this wire, no, the B field's the same because we're not asking anything about this wire. We're just asking it for the B field at the location of this.
Yeah.
But let's do it. Let's make a change and say, so any questions so far on this? Now we're going to change it to answer that question.
So for this question, we're assuming that wire 1, 2, and 3 are the ones that generating the B field, and we're just measuring it at 4.
That's right. Yeah, we're not assuming it. I mean, the question is, what's the B field here? And the B field here, well, it's near 3 wires, and so they're each going to make a B field. Just like if you said, well, there are 3 charges, plus Q, another plus Q, I don't know, another plus Q here. Find the electric field at this point in space. You know, there's an E field here from that. They each are in different directions, and then you got to find the E field from each one and then add them up. So we're doing really the same thing. So if we were to switch, let me go back to this. If we were to switch the direction of the current on this wire, let's say it goes in, so you may want a new diagram. Don't change this on your main notes because then it's going to be wrong for what's written here. But if we were to change this to be an inward current, now what would happen? Now the current is going in, and you think, well, I don't know what happens with the current in. If you think about it, a universe could not work if the directions of these didn't all switch, if the direction of the current were into the page. And you say, well, how do you know? Because if I have a current going toward you and I say the B field here is that way and the B field here is this way, well, that's fine for you standing up here looking down at it, but somebody standing under here looking at the current going away from them, they still see the same B field going around like this. It's just they see it from the other direction. And so if the current is going, if you're looking at the current going away from you, so that's here. But now if you were to stand underneath this wire, this is not new physics. This is just looking at something from the other direction. Now if I look from underneath this clipboard at the current going away from me, the B field, again, use the right hand rule, thumb in the direction of the current, the B field here points that way, the B field here is that way, B field up here is this way, over here it's kind of like that, right? And so same thing, it just switches because you're looking at it from the other side. So to answer that question from a while back, if you were to switch the direction of this current so that it went into the page, vector 2 would be replaced with this one. Okay, and so now you'd have this vector would be, you'd have mu naught, the B field here from this would be mu naught I over 2 pi root 2a, that's the size of it. And now you would have a 1 over root 2 x hat minus 1 over root 2 y hat, because now you have a positive x component and a negative y component instead of a negative x component and a positive y component. Okay, so does that answer the question? You know, so if we reverse, then you could reverse other ones too, where you could change the amounts of the currents.
Yeah, thank you. That made it very clear. Thanks.
Hang on, somebody unmuted. I couldn't hear you though.
No, I said that was good. That made it clear. Thank you.
Okay, good. And then I think, did somebody else unmute also and have a question?
I heard someone else. It sounded like a female.
Yeah. We'll take a second and see.
Sorry, that was probably just my background. Sorry.
Oh, okay. Yes, it was. Well, it's also possible somebody in the background wants to ask a question.
Maybe.
All right. So
Physics is simply so engaging, it draws everybody in.
it is.
Yep.
Okay, so let's, we're going to do another example of these, but I want to go forward and then we'll come back, you know, probably not today, but we'll come back and we'll do more examples of this. But I at least want you to see this last thing in this chapter so that next class, basically if we do it twice, it helps. So we're going to look at Ampere's law. And if you recall Gauss's law, hopefully that doesn't cause PTSD side effects in you. But if you recall Gauss's law, right, what you know is the integral of E dot dA over any closed surface is equal to the Q that's inside the surface over epsilon naught. And that was sometimes always true, sometimes useful for finding the electric field around a very symmetric object. So Ampere's law is going to be a very similar thing. It's going to tell us that the integral of B dot ds around a closed loop, so it's not a surface, it's a closed loop, is equal to mu naught times the current that's breaking through the loop. Well, what does that mean? So that's saying that, let's suppose I have a wire with current I, and we're going to do this in more detail next class, but let's suppose I have a current I coming out of the page. And let's suppose I draw a loop around it like this. So this is just this is not a surface, that's just a circle, a circular loop around it. According to Ampere's law, right, I know we already know the B field here is mu naught I over 2 pi radius. We've just been doing that, and it would point that way. And the B field here near this wire would point that way. The B field here from this would point that way. This is what we've just been doing. And so you can get the feel that integral of B dot ds around this loop, so B here goes this way, and ds, if I walk around this loop, will also go that way. So integral of B dot ds around this loop should be some sort of positive quantity. And there is current that is contained by this loop. It's current I. And so what this tells us is that Ampere's law makes the claim that these two quantities are the same, that the integral of B dot ds around this loop is equal to mu naught times the current inside it, in just the same way that if you had some charges here, and I had a closed three-dimensional surface, closed surface around it, E dot dA integrated over that surface is equal to the charge inside it. And so we'll do this in detail on Thursday, but for now, I want you to notice one interesting thing. If I have a wire with current I coming out of the page, and I make a loop like this, I want you to try to sort of guess and see what you think B integral B dot ds integrated around this loop would be. How would you even do that? Well, the B field here from this wire will point up, right? So that's at this spot, because right, I don't care that you've imagined a circle here. The B field to the right of this wire with current coming out of the page is that way. So this is B vector at this point. ds vector at this point, if I'm walking around the loop that way, ds vector points this way. So at this spot, for the contribution to B dot ds here is negative, because B is going that way, ds is going this way, because I'm walking around the loop like that. So here, B dot ds is a negative quantity. Okay, so what? Over here, the B field here points this way, because I'm still off to the right of this wire. So B goes that way. But now ds also goes this way. So here, B and ds go the same way, so B dot ds is positive. So, and as I walk around, it's going to be different values at all places. Like here, B vector is going to point that way, ds vector is going to point that way, and so it's going to be very small, the dot product, because they're almost perpendicular. And so I don't know, I'm going to get some near zero contributions, some positive contributions, some negative contributions. I don't know how that'll all work out. Ampere's law tells us that if you were to integrate B dot ds around that loop, you'd get zero, because there's no current inside the loop. And so what I want you to, right, we're not doing integration yet in this, but what I want you to see is something interesting that happens. As I move this wire, let's say I grab hold of this and I gradually move it closer to this loop, think about what happens, right? So here's my loop, and here's my wire with current I, and I'm going to keep moving it closer. As I move it closer, right, I'm still always going to get, when this part of the loop is to the right of the wire, I'm always going to get B and ds pointing in opposite directions on this side of the loop. But look what happens. As soon as this current I crosses the boundary and is inside, now when you're here, B points that way and ds points that way. So as soon as you jump sides, this crosses into the loop, now B and ds generally point the same way all the way around. And so you would expect to get a positive integral for B dot ds. When it's outside, you'd sort of maybe expect to get zero. It's the same thing with Gauss's law. If I have some closed surface, if I have a charge here, if I'm here, there's an E field that goes inward. So there's inward flow of electric flux because dA points out. And over here, I get E field and dA point in the same direction. So I have outward flow of electric flux. And that'll be true no matter where I put this charge. But as soon as the charge crosses into this closed boundary, as soon as it crosses in here, now E and dA always generally both point outward. And so it makes sense that it's the charge inside that contributes positive amounts to this integral. The charge outside doesn't contribute anything to this integral. All right. So on Tuesday, we're going to do quite a bit with this, but be sure you study it before class on Tuesday because it's a subtle, these are not easy to do. I mean, they're easy
Professor-
once you get the hang of them, but they're tricky at first, okay?
What is DS one, and why is it always going counterclockwise?
So DS is a small step around the loop. You can make it clockwise. We'll talk about that later. You can choose either direction you want. But I just happen to choose it this way. So DS means a small step around the loop. Okay? In the direction that you've decided to walk. Other questions so far? Okay. All right. So be sure you take some time to, when you're reviewing what we did today, be sure you take time to really study Ampere's law before Tuesday, because you want to kind of be familiar. You should have worked through examples of this before class Tuesday. Okay. And otherwise, have a good weekend. Yes, there are office hours today. Yep.